Hi everyone, welcome back to our machine learning course. I'm Joaquin van Schoren and today we'll talk about convolutional neural networks. So we'll start by explaining what an image convolution actually is. Then we'll talk about how to build neural networks out of them. Then we'll talk about things like data augmentation, how we can build more data to have more training data to train models with. Then we'll talk about how real-world CNNs are built. Then we'll talk about how we can look inside the model to see what they've learned. And then finally we'll look at pre-trained networks and how we can transfer from them to build new models for new problems faster and better. Okay, so first of all, what's a convolution? A convolution is a very simple operation where we multiply one small part of an image, let's say this part of this input image here, with another small image called a kernel, this guy here, right? And so what we'll do is we will take this image, which is a 3x3 patch of the image, and this kernel here, and what we'll do an element-wise sum. So we'll take this value times this value plus this value times this value plus this value times that value, and so forth until this value times this value. And then we sum everything up, and that's our output pixel. That's the value we'll see over here. This is 1 pixel out. And so to do a full convolution, we need to move this kernel across this image. So we cover every part of that, and as a result, we'll get output pixels as well for the output image. And so this way we can transform an input image into an output image in a certain way. And what way? That's defined by a kernel. So different settings for this kernel, different values inside this little matrix here, will cause different types of output. This particular guy is a diagonal edge detector, so it will detect whether there's like a diagonal edge in the image, and you will see that indeed diagonal edges are highlighted by this particular filter, right? Very simple operation, but very useful for machine learning. Before we go further, I will give you a very short demonstration. What will happen? So say I have my original kernel, say take a simple horizontal kernel, and we move that over the image. Nothing will happen for a while because these are all zeros, so we also get all zeros out. Nothing will happen until we hit the first non-zero value here, right? And now we see we get some outputs. So these are already 5 different outputs, right? Because at this point, the bottom of this kernel hits some non-zero values, which means that we'll sum up these positive values and we get some positive value out in the center, right? And so this particular kernel reacts when there's something at the bottom and there's nothing on top, right? This is an horizontal edge, right? So and then you will see it will actually give you a positive output. And if you move this guy further and further, we will see that it will respond over values. If you have like a bottom edge, like here, what will happen? Well, it sees nothing at the bottom, so no positive values, but it sees something at the top, so it gets a negative value, so we get black negative value out. Right, so this image, gray is 0, white is positive, and black is negative. And so we'll see that for top edges, we'll get a white output. For the bottom of an edge, we'll get a black output. Right? And so this way, this particular convolution will highlight all horizontal edges it will see in the image, meaning every part of the values here where there's something on top or something on the bottom, nothing. Well, when there's something in the middle and nothing on top, or something on the bottom, or vice versa. Okay. Other kernels will do different things, like a diagonal kernel. If I run that over the image, we'll see. Well, it will particularly react to diagonal, meaning in this direction, edges exist. Like this edge here will highlight because it's a diagonal edge. Right? And the same at the bottom here, this guy also reacts because this part is very clearly a diagonal kernel. So every time when there's 3 pixel values on the diagonal which are positive, they will get a more negative output. So that's why it's here black. Another one could be edge detect. This will react to any edges. And again, we'll get a negative value in the middle of an edge and positive around it. Right? And so all of these convolutions will highlight different things in the image. And this will tell us something. It will tell us whether the image is composed of a diagonal edge or a horizontal edge or something else. And this information, like knowing that certain types of edges exist in the image, will help us identify what kind of image it is. If we know, for instance, that a certain number, like in 0 or 1 or 2, in this case, has certain kinds of edges, we can from that deduce whether the number is actually positive or negative. Right? We won't deduce that directly, but the information that certain edges are there is useful to have a simpler representation of the image that we can then use to make predictions for, or we can learn a model that can then map those pixel values to an embedding, and the embedding then to an output. Okay. Good. So let's go to a more real-world example. This is the fashion MNIST dataset. So here we have different small images of garments like ankle boots or t-shirt tops, dresses, pullovers, sneakers, and so on, right? A little bit more complicated, so let's see how that looks if we do convolution over it. Same thing we can do here. So if you run this horizontal edge detector to it, we can see, okay, where in the image are the horizontal edges, where in the image are all the edges. So you can see so increases in the dress here, or where are the diagonal edges, right? And all these things, again, they will tell us what kind of edges exist in these images, and it will help us to later on classify what kind of image it is. Now, how do this in practice? Because we can invent an infinite number of kernels, right? So how do we know which ones are useful for the type of image we're looking at, right? Well, for a long time, people have been developing families of these kernels, also called filter banks. The most famous being, for instance, Gabor filter or Sobel filters or hair wavelets, and you can run all those families of kernels over the image, get different outputs, and from that we can hopefully classify those things better. And let's look at one particular example called a Gabor filter. A Gabor filter is defined by three values: the frequency, that's the frequency of the wave that we want to find, theta, that's the angle, and sigma, the resolution. So let's see how that looks like. So this is my filter. It's a larger filter, right? It's not 3 by 3. It's quite I don't know, like a 9 by 9 or 11 by 11 filter. And these different values, they will change the image in certain ways, right? So this is resolution. So we get larger filters or a smaller filter, right? Theta is the angle. So here we have horizontal waves. We can also make it diagonal waves, right? And frequency is the frequency of the wave. So it can be very wide or very narrow. And so with these three variables, we can create all kinds of filters. And by doing that, we can get all kinds of responses for a certain input image. So if you take our dress here and we play around with this, then we can, for instance, let's take it smaller. So now we can, for instance, see what kind of edges exist in the image, right? And we can see as we move theta, we can see different parts of the image light up in the output, which may tell us something about what kind of image it is. Right? And so not all of them are useful, some of them are. Okay, so and you can run an entire filter bank of those filters over it, and we'll get different outputs. And the idea is that by having many different representations of the image, that each of these will tell us something about the image, and by combining the right pieces of information from the input, we can then deduce what kind of class of image it is. Right? And that's the whole idea we do always with neural networks. Neural networks are very good at identifying what parts of the input data help us to to give the correct output classification, right? And we learn that mapping between all those different inputs and the output. And the idea here being that pixel values themselves are not very informative, but if we can identify certain aspects which are important in the image, then from that we can learn more easily what the output class could be. Right. Now, people have been trying this for a long time. This sort of works, but it's not always. There's still a lot of useless mappings made here that are not so useful, right? So we may want to do something more clever later. And of course, the more clever way will be convolutional neural networks, which we will discuss in the next video.